First off, I want you to think about how weight is a factor in so many of your designs. We often need to reduce weight of our designs to reduce material costs or shipping costs, or we need the performance benefit of a lighter design. Over the next 30 minutes or so, I'm going to show you how to use the new topology tool that was introduced this year in SOLIDWORKS Simulation 2018 to help you optimize your designs, particularly when it comes to reducing weight or increasing stiffness to weight ratios. We'll discuss what topology optimization is, how it can benefit us. We'll compare it to design optimization study. I'll show you how to set up a study, including looking at all the different options and how those options affect our results. We'll discuss some tips and tricks, and then I'll answer any questions you have. But please feel free to submit a question to me throughout the webinar, as we'll be checking those as we go. But first off, I want to thank you all for attending this webinar, and I want to introduce myself. I'm Doug Enns. I'm one of our application experts here at MLC CAD Systems. I'm a professional mechanical engineer with about 30 years of design experience. And as I think about all the designs I've been a part of, increasing the stiffness to weight ratio has been crucial to the success of many of those designs. So I want to start with our first poll question. So our first question is, for the products you design, is weight an important factor? And so most everybody, it looks like, is saying, yes, it is an important factor. And it looks like for nearly half of you, it's due to cost reasons. And about a third of you, it's for performance, or performance and cost, I should say. And about 11% looks like performance. So, but the vast majority of you, weight is a factor. That's good, because I'm going to be showing you how the topology study can really benefit us as far as reducing part weight goes. So for our topology discussion today, I'm going to be optimizing the design of a bicycle component. And to these pro cyclists in this picture, every gram is important. The guy in yellow, he's a time trialist and a climber, so he's worried about the weight of his bike. But the two guys behind him, Mark Cavendish and Peter Sagan, these guys are sprinters that are hitting speeds of over 45 miles per hour in the final sprint. And in doing so, they're putting a tremendous torque on the handlebars, which is then transmitted through the handlebar stem to the rest of the bike. So these guys, the sprinters, they're not only worried about the weight of their bike, they want the highest stiffness to weight ratio. The less the stem flexes as they're cranking on the handlebars, the more power they can generate. So for our task today, we're going to try to improve the stiffness to weight ratio of the typical racing bike handlebar stem, shown here in green in the image. Now, this is a stem design that's been used for about the last 20 years, and it was designed to already have a high stiffness to weight ratio. So improving this design may be a challenge, but we're going to see how the topology study can help us. Before we start the topology study, let's discuss the progression of simulation, starting with the more manual approach and then looking at more automated approaches. So SOLIDWORKS simulation, I assume most of you that are joining this are simulation users already, and so we know it's a powerful tool giving us FEA analysis right inside of our design software. So we can look at different design scenarios quickly and ensure they meet our design requirements before we ever spend that first dollar on prototyping. So the first step in automating the design optimization process in simulation is by using Trend Tracker. So Trend Tracker allows us to track and graph things such as change in weight, stress, and displacement as we manually make changes to our model. Trend Tracker is useful. It's a useful tool to help us keep track of those design changes, but making the changes is still a manual process. We're still manually modifying the model and then rerunning the simulation. So the next step up in automating the optimization of our design is by using the simulation design study. Design studies, they're based on a parent study and automate the optimization of either a part or an assembly by changing specified dimensions or parameters in our model. So in this bracket is loaded across the top and it's fixed at those two mounting holes. And we specify the constraints for a design study giving a maximum stress or displacement or minimum factor of safety. And then we specify a goal, such as minimizing part weight. We pick the dimensions that we want to modify and give each of them a range. SOLIDWORKS then automatically varies all the dimensions and looks at the results of each of the scenarios and selects the optimized scenario. Even modifies the model, showing us the optimized scenario. In this case, it's the one with the minimized mass. So design optimizations are a great tool for automating the optimization process if we have a good idea of what the dimensions need to be changed to. So we have to specify which dimensions we want to change and what range we want those dimensions to be changed within. So we have to have some forethought in what the final design should look like beforehand. And the output we get in the design study remains parametric. It's only changing those parameters that we told it to change. And so there is some limit as to just how optimized our design can get. So finally, we have the topology study. It's kind of like a design study on steroids. It was introduced in SOLIDWORKS Simulation 2018, as I mentioned, and it's available in the Simulation Professional and Simulation Premium packages. Shown here is that same bracket that we were just looking at from our design study after a topology study has been run on it. As you can see, we're getting a non-parametric optimization of our part. The software will organically remove the mass based on where and how the loads are transferred through the part. So elements that don't contribute significantly to the overall stiffness of the part are getting removed. In a topology study, we don't have to have features or dimensions defined for the shape to be adjusted, meaning you don't have to know what the final design should look like before you start the study. We can start with just a simple model of our maximum design space, which is what I'm going to show you in a minute, and define our features on loads, and then let topology show us what the optimum design should look like. So I'm going to, before I go into SOLIDWORKS, I want to look at our second poll question. How do you ensure your designs meet requirements? Are you building and testing prototypes, performing a simulation on multiple design studies, or are you already using the design study or topology study? So it looks like about half of you build and test prototypes, the other half are using simulation. Doesn't look like anybody's using the topology study yet, and it's brand new, so hopefully after this discussion, maybe you'll give it a try and see how it can benefit you. And let's go into SOLIDWORKS and start our task of optimizing the stiffness to weight ratio of this handlebar stem. So here's the original design. What I've got is I'm fixing my traditional handlebar stem here where the stem of the fork mounts to it, and then I'm applying a load on each side. I've got a 150-pound load pushing downward 200 millimeters from the center of my stem. That's out at the end of the handlebar. And on the other side here, I've got an upward, I'm pulling up on the handlebar at 150-pound load. So I'm really torquing on that handlebar. And I've run this study, and I'm getting a displacement of about 30 thousandths of an inch. So that's 30 thousandths on the outside of the stem. By the time you get out to the end of the handlebars, that's about nearly a 200 thousandths displacement, 200 thousandths of an inch displacement. So quite a bit of flex there in that stem. And so if we were to use a topology study, we could take this existing design and go straight into our topology study. And here I'm going to show you one. I'll talk about the setup in just a minute, but what I get in a topology study is I get this, what we call a material mass plot. So it's going to show me here what material can be removed. You can see the material that's being removed here up on the front of the stem, and everything in purple is material that we can remove. And so right away I can see there is some material I could reduce the weight a little bit, but this is based on just increasing or improving, I should say reducing the weight of an existing design that's been around for 20 years. And we can improve it a little bit, but I think we can do better. We can do better by starting with what we call our maximum design space. And so that's what I've done. Keep in mind, this design was flexing about 30 thousandths of an inch, but I've got another configuration showing my maximum design space. And so here I know where the fork stem is connected to my handlebar stem. I know where the handlebar is. I know where my bolt holes are. So I've got all that modeled in, and then I'm just modeling in geometry of what I'm considering my maximum design space. I don't want this stem to be any bigger than this. And so I'm going to start there, and I'm going to start my topology study. So starting a topology study is a lot like just setting up a static study. I'm going to go start on new study. And down in my design insight plots, in addition to the design study that's been around a while, I now have a topology study. So I'm just going to start my topology study. And the setup, I'm just applying my materials, my fixtures, my loads, much like I would in a static study. In fact, I'm just going to go to my static study, and I'm going to control select my material, fixtures, and loads, and just drag those down to my topology study to copy them in there. So in my topology study, I've modified those spaces. So let me just redefine those loads. But basically, I've got the same 150-pound load pushing down on one side and pushing up on the other side. So there it is. I've set it up just like a static study. The difference is I then define my goals and constraints. So I can either define a best stiffness to weight ratio, a minimum displacement in my model, or I can minimize the mass of my model given some displacement constraint, given some maximum displacement that I will allow. What we're going to do is we want the best stiffness to weight ratio. So just click that. And I want to reduce the mass of this part. I'm going to say by 80%. I could add an additional constraint to specify a maximum displacement, but I'm going to leave that unchecked for now. And just specify my best stiffness to weight ratio. And there I am. There I am. I've got it to where I can go ahead and just run the model. Now, if I run it now, I'm going to get a optimized shape, material mass plot, but it may not be something that's very producible. So what I want to do, I want to come down here and add some manufacturing controls. So I've got several manufacturing controls I can apply. The first is adding preserved regions. So I'm going to do that first. And everywhere I have a bolt hole here, I'm going to go select all the faces where my bolt contacts my part. I've already saved these as a selection set. And I'm going to specify that from 1 millimeter out from that face, I'm going to preserve that region. That region is going to be frozen, and none of the elements in that region are going to be removed during the topology study. So you can see a little preview of the areas that are going to be preserved. It's also going to preserve automatically the areas where I've applied a fixture or a load. But that can be controlled in the settings, and I'll show you where we control that. But by default, it's going to preserve that face there where I'm applying the load, and the same on the other side in that fixed area. So I'm going to accept that. The next manufacturing control, I can specify a thickness control. So as it kind of builds those webs, building my structure in the topology study, I can specify a minimum and or maximum thickness for those webs. I'm going to leave that untouched. I'm going to come down here to specify a symmetry plane. So with symmetry, I can do half symmetry, quarter symmetry, or eighth symmetry. So eighth symmetry, for example, maybe I want this to be symmetrical about the front, right, and top planes. For this model, though, obviously I don't want it symmetrical about that front plane. I could do quarter symmetry and make it symmetrical about maybe the top and the right plane. But what I'm going to do, I'm not worried about the top and bottom of this being symmetrical. So I'm just going to go to half symmetry and pick that right plane. So now the right side of my handlebar stem and the left sides of the stem are going to be symmetrical, and that's what I want there. So I'm applying my symmetry control. And then the final manufacturing control I have is the demold direction control. So I'm going to go specify a demold direction, and I've got 3 options here. So I can specify a mid-plane, looks like that. I can specify a pole direction, or I can specify a stamping direction. I think the best way to show you how that affects our results is go back to that bracket that we were looking at. So here's that bracket after our topology study. This is what we were looking at after a stamping study. But we basically have these 4 different options for our demold control. We can apply no demold control, mid-plane control, stamping, or a pole direction. So let's look at what our results look like if we don't apply a demold control direction. So we're getting that part there. You can see it's kind of hollow on the inside. And so we're getting an optimized shape as far as stiffness to weight ratio goes, but it may give us a result that's pretty hard to produce using traditional methods. Like that would be a pretty difficult part to machine since it's all hollow on the inside. If we go add a mid-plane control, we'll get a part that looks like this. So it's got the mid-plane and then material is removed outward in both sides. If we apply a stamping control, we get this part here. It basically has through holes in it. Material is being removed in the direction that we specify all the way through. So we could produce this part using a stamping process or maybe a machining process that we could machine all from one side of the part. So that's a stamping control. And then finally, we have a pole direction control. In this case, we pick a plane and the material is removed in one direction from the plane. So this would maybe give us a part that is easily injection moldable. It would be easy to remove this part from the mold. So what we're going to do in this this part is I'm going to use a mid-plane. So when you do this, I recommend you try different options. I'm going to do the mid-plane control. So it's going to, I need to define an edge. So in this case, I'm going to pick a vertical edge here along the Y direction. And so it's basically going to put holes going up and down through this part in the Y direction. So I've got all my manufacturing controls. I'm ready to mesh the part. When I create a mesh in a topology study, mesh size is pretty important. And so the default mesh size is actually quite a bit smaller in a topology study than it is in a regular static study. But I recommend you start with that default mesh size. I'll show you how that can affect our results. So here's that study of our bracket using the default mesh size. If I use a coarse mesh size, you'll see I don't get nearly as nice a results. So I recommend you keep the mesh size at the default to start with. And you'll notice by default also that we're using draft quality elements. So the draft quality elements in our topology study, we're looking at displacements rather than stresses. So the draft quality element is still going to give us reliable results as far as displacements go, but they're going to really reduce our solver time versus using high quality elements. So I recommend you leave the default setting and leave the draft quality mesh as the default. So I'm going to go ahead and mesh that, and you'll see if you run a lot of studies that this is a pretty fine mesh compared to what we get with a default static study mesh. And the last thing I want to do before I run the study is I'm going to go click up on the study name here and go down to properties. And so the Intel Direct Sparse solver is a good solver for topology studies, but when in doubt, use the automatic solver selection. Let SOLIDWORKS determine which solver is best. It's going to do that based on geometry, the type of study you're running, the materials in there. So go ahead and let SOLIDWORKS to determine which solver you're using. I'm going to use the Intel Direct Sparks though, and I'm going to come down here and define which regions get preserved. So by default, as I was mentioning, it's going to preserve the regions with loads and fixtures. So these faces here in my model, where I've got the loads and fixtures, no elements are going to be removed from those faces. But I could turn that off to where it does not do that, or I could have it preserve only the regions where I'm applying loads, or only the regions where I'm applying fixtures. But I'm going to leave that at the default setting of loads and fixtures areas being preserved. So with that set, I'm ready to run the study. So I just right click and hit run. Now, this being an iterative process, this study, I've run it ahead of time. It takes about 10 minutes to solve. Of course, with a much finer mesh size, it's going to increase that study time. But this one took about 10 minutes to solve, and I'll show you the results that we get. We get our material mass plot. So I'm going to edit the definition of our material mass plot, show it here. So there it is. It's removed all the elements from that original model that did not contribute significantly to the stiffness of that part. So I can make that lighter. Look at that part. So a lot thinner walls there. Or I can make it heavier. So a little thicker walls there. And once I'm done, I can calculate the smooth mesh. So there's my smooth mesh of my optimized design. So once I've done that, I can now right click on the material mass plot and I can export that smooth mesh. So I can export it either to a different configuration of this part or to a completely new part file. And I can choose to export either just the graphics body. I could export the solid body. Maybe I just want to export it to a solid body and print it on a 3D printer. Or I could export just the surface body. I would typically choose to just export the graphics body to a new part file. Then I can take that graphics body and use that to create sketches around that graphics body that I can then use to build my new part file. So I would export the graphics body and redesign my part file. You'll notice I get other stress plots. I can create stress plots, displacement plots, and strain plots of my topology study. But as you'll notice, I've got this little warning here saying that these are only a rough estimate because let's look at one of these, like a displacement plot, for example. They're looking at the displacement of the entire original model, so the original body. And so only use these as a very rough estimate of what the displacement might look like. What we want to do is use our exported smooth mesh to create our final design. And so that's what I've done here. I've created a new model around that exported mesh. And once I have this model created, now I want to rerun my simulation studies. On this one, I'm going to start with a static study. I probably want to look at a frequency analysis and a fatigue analysis on this part, but I'm going to do that of my final design. And so here's my new part. I've run a static study already. And on this part, as you recall, the original displacement was about 30 thousandths of an inch. And now this new design only displaces 20 thousandths of an inch with the same 150-pound load on each side. And so we've cut down our displacement by about 33%. So it's like much stiffer than it was before. And that's a part that's considered to already be optimized and is currently the design being used in racing. So we've reduced the displacement by 33%. And if I look at my part weight, the original design was 280 grams. This new design is 243 grams, so almost 40 grams lighter. And so what we get is, we're taking a part that's already considered to have a high stiffness to weight ratio, and we're able to increase its stiffness while reducing the weight by almost 40 grams. And if you look at the final design, that is a shape that I probably wouldn't have come up with on my own. I could have tried a lot of different iterations before coming up with anything close to this. The design, the topology study came up from just my maximum design space. So it's kind of helping me design that part for me. Oh, I should mention, I did that all as a single part, and then I came and split it after the fact. The topology studies do only work on single part files, not on assemblies. So, but anyway, I think it's really cool that it's giving me the optimum design when I just give it the maximum design space. So now some tips and tricks. I recommend starting with the maximum design space, as I mentioned. You can start with your existing design, and yeah, you may see some ways you can remove some material, but starting with that maximum design space is going to really have the topology study kind of design that optimum part for you. And then once you have that design space set up, run a static study to validate your setup before running the topology study, because your static studies run a lot quicker, and it'll let you validate your setups, your loads and your fixtures before going to the trouble of setting up your topology study. Then you can just copy your materials, loads, and fixtures over to that topology study. Start with the best stiffness to weight ratio as your goal. Once you've run that topology study and redesigned a part around that, you can always rerun another study to minimize displacement or minimize weight. So look at the topology study properties before running the analysis to make sure you're preserving the regions automatically that you want to, and that you're using the correct solver. As far as solvers go, using the automatic solver selection is pretty much always a good idea, but the Intel Direct Spar solver provides faster performance, especially when looking at multiple load cases. So in a topology study, we can look at load cases like we do in the static study. The difference is it does not give you a deformation plot for each load case. It looks at all load cases combined and then gives you one single a material mass plot for all load cases, one plot for all load cases. So it is a little bit different. And I should mention the topology studies do not support the use of the Intel Direct Spar solver. But again, there is a knowledge-based article about the solvers, but use the automatic solver selection in most cases. And try different manufacturing controls to see which gives you the best outcome. I was using the pole direct or the demold direction, but here's the same study when using a stamping control direction in the X direction. So it put through holes basically in the X direction, really giving me a totally different result. So try different control methods to see which ones give you the results that are most desirable. And then use the topology results as a blueprint for creating your final design, meaning you do need to create that final design to run your study. So don't rely on the topology stress and displacement plots. You've got to run your analysis on your final design to ensure it's going to meet design requirements. And then use the draft quality elements, which are there by default. And the quality of the mesh is important, as I showed you in those two images of that bracket. So I recommend you start with the default mesh size, and then you can reduce that mesh size from there to look at how that affects your results. And then SOLIDWORKS does recommend using the standard mesher over the curvature-based mesher. I have used both, and both seem to work okay for me, but that is a SOLIDWORKS recommendation, is to use the standard-based mesher. And I appreciate you attending. That's the end of our webinar, but I'm going to stay connected for the next couple of minutes in case anyone else has some questions. But thanks again. Thanks for your time.